Okay, now I'm afraid, if you're taking notes, you're going to be stuck here because I've just copied the picture from the notes, but of course you'll see it on the scan. Don't try and copy this down now. So there is a network of roads, if you like, or whatever the application is. And we're going to start from S. We're trying to count. First of all, we're not going to worry about the second row. We're just going to look at the first row. So we're going to define AN. I'll just talk you through the essence of this. We're going to let AN be the number of routes, the number of different routes. Obviously these are directed routes from, say, arrows, one-way streets. The number of routes from S, the starting point, to Pn on the first row. Obviously if n's bigger than 7, you have to continue the diagram. So what's A1? How many ways can I get from S to P1? 2. Correct. Because I can either go vertically upwards or one across and backwards. I can't get to P1 any other way because the arrows come out of P1, these black arrows. So it's just 2. And I'm going to later on, I probably won't get to Bn, but I'll give you the result. Bn is the same number to points on the top row. Okay, so that's the setup. And we want to find formula for AN and Bn. So how do we do that? Well, let's look at, this is coloured red, this bit, because I'm actually trying to look at P5. No, P6. So let's study P6. Let's just do an example. How can we get to P6? Okay, well, to get to P6, we need an incoming arrow. And the incoming arrow, there are 3 incoming arrows. So we can come from P5, or we can come down from the bottom row. Now, if we come from the bottom row, the number of ways to get to this point here, there's only one way, because we can only just keep going across from S horizontally to get to this point. There's no other way of getting to this point. Okay? So it's just one route to this point. So I can't come back to this point. So there's one route from here. If I go one further horizontally, I can also get to this point, but there's no other way of getting to this point. But then to get to P5, we don't know what the number is, but it's what we're trying to find. So we see that in this simple case, the number of ways of getting to P6, that's A6, you can do it in 3 different ways. Either you can come from below in 2 ways, or you can come from the left from P5. And there are A5 ways of getting to P5. So we get that relationship. And that's going to be typical. There's nothing special about P6 after you start. Well, if you like, P0 is 0, so this would also be true for A1. So the relation is that this will show you that AN, the recurrence relation for the sequence AN, is a very simple one, namely that AN is equal to AN minus 1 plus 2. That's what I've proved. Very, very simple recurrence relation, and we can solve that and find how many routes there are to each point on the first row. Now, what's the solution of this recurrence relation, given that A1 is also equal to 2? What's the solution of this recurrence relation?
2n.
Yeah, 2n. Now, you could have solved it if you didn't know. How would I have solved it? I'd have said that the recurrence relation is AN is equal to AN minus 1 is equal to 2. I'll do this because people are a bit confused, I think, about my concept of a constant sequence. So let's just, it's pretty obvious 2n will work here, because if A1 is 2, A2 has got to be 4, A3 has got to be 6, and so on. So the general answer is 2n. But if we just use the theory, we'd write down the occurrence relation like that. This is a first order equation. It gives us a polynomial, which is lambda minus 1. So the root is 1. So the general solution of the homogeneous equation is obviously an is equal to 1. an is equal to the root, is a constant, times 1 to the power n. Okay, but if we've got the homogeneous equation, they're all equal, and the first one's equal to 2, so obviously a is equal to 2. This is the general solution of the homogeneous equation. So if we want a solution of the non-homogeneous equation, we can't choose a constant because that's the solution of the homogeneous equation. So we have to choose, essentially, we have to multiply. We would have chosen a constant. So for the non-homogeneous equation, we have to try an, or I called it Pn as a particular solution, but I'm substituting that in as an, and that would have to be some constant times, a constant on its own is not enough, we have to multiply it by n. So we try a constant times n. So we just substitute that in to this equation, and this is terribly long-winded, but it illustrates our method. So we substitute that in, we get alpha n is equal to alpha n minus 1 plus 2. Okay, now of course we know that the n's have to cancel out, otherwise we'd have made a mistake. And so what does that tell us? It tells us that 2 alpha is equal to 2. I made a mistake, have I?
It's minus alpha plus 2 equals 0.
By which line am I wrong here?
The very bottom, just the very bottom one is
Oh yeah, there's no alpha here, sorry, that's 0, quite right. Alpha is equal to 2, sorry. This is 0. Alpha is equal to 2, which of course means that our particular solution is, well, it means that our particular solution is 2n, so Pn is 2n. I shouldn't have said a is 2 here because I was solving the homogeneous equation. I should have just left the a there, and then we get a is equal to 0. So the final solution is 2n. Okay? I mean, this is really ridiculous because it was obvious, it's completely obvious, it should be obvious that the solution of this recurrence relation, if a1 is 2, an has to be 2n. But I just went through the theory. And I even made the mistake of trying to put this constant in before I got the particular solution, which was a mistake. Okay, I should have just left this as a times 1. Okay, so that's the particular solution. The general solution would have been that plus a constant, but that constant has to be 0, otherwise we don't satisfy this relation. Is that clear? So an or Pn is 2n. So the conclusion here is that an, the number of roots to p, the number of roots to Pn is 2n. Now that's easy enough. What about Bn? Well, I don't have time to go through the details, but let me just tell you how you do that. So let's look at the picture again. So let me leave that for a moment. Can I just pause and ask everyone, is the method clear here? Just this example is very simple, but it does illustrate the general method to solve a recurrence relation. Okay, so we try a particular solution. We have to multiply that by n because otherwise it would have been a solution of the homogeneous equation. We find the value of the constant. We then, strictly speaking, we should then take that particular solution and add on the general solution of the homogeneous equation, which was just capital A, but then when you substitute in the initial condition, you find that this constant capital A is 0, so that gives you the final answer of too many p's around. This Pn was for a particular solution, probably best to call it An, so as not to confuse it with the point. Now, what about the b's? Well, we have to go back to our diagram, which is here, and try and find how can I get to a q. So let's start again and try and see what we can say about Bn. This is all explained in the notes. Now, let's see, I haven't coloured anything here. So how can I get to, say, Q6? Or let's do Q4 to get out of the way of the other stuff. How can I get to Q4? Well, I can get to Q4 by coming from Q3, or coming from P4, or coming from P5. Okay? With arrows in those directions. So I can come this way. So that tells you immediately that in general, it will be, well, let's do it for B4. B4, therefore, is equal to the number of routes to Q3, that's B3, plus the number of routes to P4, that's A4, plus the number of routes to P5, which is A5. So that's the recurrence relation for the B's, or for one lot of B's. Okay, so more in general, we get that Bn, obviously the same argument will apply for Bn, as long as n's large enough, well, at least one, I think it needs only. It's going to be, no, I need probably two here, because I've got to be able to go back one. So it's going to be Bn minus 1 plus An plus An plus 1. That's going to be the general form of the recurrence relation for the B's. But we know what the A's are. Okay, so all the A's are, what is this? So that's equal to Bn minus 1 plus 2n, that's what we showed, plus 2 into n plus 1. That's what the An is 2n, so An plus 1 is 2 into n plus 1. So that's equal to Bn minus 1 plus 4n plus 2. So that's our recurrence relation for the B's.
If n is a finite number, aren't you not going to have the last, if you go up, there were like 3 choices. If you want to do the last one, so for example in Q7.
No, this diagram goes on forever. Is that your question? You're worried if I'm at the end of the diagram?
Yes.
Yeah. No, it would be a bit more complicated. You'd have to do a special case. The diagram goes on forever. Okay, so there's no last. The roots, it's an infinite sort of... Okay. I'm assuming the diagram, I've just done it up to 7. You're quite right, of course. I'd be stuck. This is not correct for... With the given diagram, it wouldn't work for B7, but I'm intending here that the diagram goes on forever. Okay. Otherwise, it's more complicated. Okay, and then I'll leave it as an exercise, because I don't want to muddle it up again. It is a very simple recurrence relation. Again, you have a constant solution of the homogeneous equation. That tells you that to guess a particular solution, you're going to have to multiply by n. So you would expect a quadratic particular solution. And in fact, Bn turns out to be, this is an easy exercise, 2n squared plus 4n. Sorry. Let me just say that again so it's hidden. Here's our recurrence relation. Again, because Bn is the homogeneous equation, it's just simply saying that the terms of the sequence are all equal. So that the solution of that is a constant. If all the terms of the sequence are equal, that means that the sequence has to be a constant sequence. So the solution is just a constant. Okay, that means that when you're guessing a particular solution of the non-homogeneous equation, there's no point adding a constant. So your guess would have been a polynomial of degree 1, but you have to multiply that by n. So you end up with guessing an squared plus bn, and the answer is that bn is equal to this. Okay, so that counts. That's just a typical example of an application of recurrence relations to counting roots on a network.